Okay, so the recording has started now. Now I'll share the screen. I hope you are able to see my screen, right?
Yes, sir.
Okay,
Am
okay.
I audible, sir?
Yeah, you are audible. So this is basically the NPTEL CS52 Reinforcement Learning course by Professor Balaraman Ravindran from CSE Department in IIT Madras, and I am a PMRF TA from CSE Department IIT Bombay. My name is Sandarbh Yadav, and this is the week 4. This session is being conducted on 20 February 2024, which is Tuesday. So generally, like these sessions are on Tuesdays. So there are three parallel sessions going on, one on Saturday, one on Monday, and one on Tuesday. So this is the session on Tuesday, and it's from 6 p.m. to 8 p.m. Same link. Like I have attached the link here. And anyone who has taken this course can attend these sessions. So the discussion will be on practice assignments and the assignments, and we will do some problem solving and doubt clarification also. These problems will be different from the problems in practice assignments and assignments, and the goal of these sessions is to enable two-way communication. Generally you have been given recorded videos for uh, like the actual lectures, but these sessions ensure that you will have two-way communication with us also. So the expectation is that again that you should have watched the weekly lecture videos before this session. So week 4, all the lecture 6 lecture videos you should have watched, and at least made an honest attempt on weekly assignment and practice assignment. And it is recommended to read Saturn and Bartobo. Also, like I'll be sharing the slides and recordings. So are you able to access those slides and recordings?
Sir, I have not tried to access it.
Okay, okay. So maybe like, do you want me to show how to access?
Uh, Sir, now the requirement is not there, but
Okay,
I don't know in the future. Maybe.
okay. So maybe I'll like some people might be watching it on the recording, so I'll like share it just once. Maybe I'll share the Mozilla. So this is the like NPTEL page. In this, like you can go here problem solving session, and then in solving session recording, like here you will get a link. So when you click this, click here, then you will be directed to an Excel sheet. In this, like we are uploading the videos also, and this Google Drive folder, like it contains all the slides and codes, whatever is there. And this is for all the three TAs who are conducting these sessions. So now I'll go back to the slides. So the general guidelines are to keep yourself muted as always. Like if you have doubt, you can unmute and ask. Otherwise, just write in chat and try to solve problems with me. I'll be giving time when needed. And the order is first we will solve the practice assignment, then solve some problems which are not part of practice assignment or assignment. And then like in between, I'll show a demo also. Like this week, I'll show demo on value equation, and then we will solve the 10 questions of assignments. So in assignment, I won't give you the exact answers. So you have to like kind of find your way to the answer, but I'll guide you through. So audience interaction, I think like this we have done enough. So these are the like week 4 topics. So the topics were MDP modeling, then Bellman equation, then Bellman optimality equation. Fourth section was Cauchy sequence and Green's equation. Then fifth section was Banach fixed point theorem and its proof. So let's begin with the practice assignment first. So the practice assignment first question is like, so basically what I have felt is that this week's assignments, also the practice assignment and the assignment are quite easy. So you guys should be able to do it, but either way, like we will do it one by one. So the question first is it true or false? The Bellman optimality equation. So the key term here is optimality can be solved as a linear system of equations. So is this like true or false? Maybe you can write and check. Like this is quite simple. Like, but the key thing to note is like it's optimality equation, not just Bellman equation. So maybe I'll check and check once. So yeah, false. So the reason why this is false is like, like in Bellman optimality equation, there is a max operator in the beginning. So this max over actions, like it makes it like non-linear. So it cannot be solved using a linear system of equation. But if the question was like just Bellman equation, then definitely it can be solved using a linear system of equation. So the answer is false. Now, I hope there is no doubt in this. So the second question which we have is consider the following statements for a finite MDP, and p pi is the stochastic metric. So basically like this contains probability of transition, and this is the same like matrix which was discussed in the recorded lectures also. So the Bellman equation for the value function of a finite MDP defines a contraction operator using the max norm. Yes, it does like define that contraction operator. And what was that contraction operator? It was L pi. And if like z, then if gamma is between 0 and 1, 1 excluded, then the eigenvalues of gamma p pi are less than 1. So basically like the special property of this p pi matrix is that the like it will have some eigenvectors, suppose e1, e2, some ek eigenvectors. So the maximum of these eigenvectors, so maybe I'll take max here. So maximum of these eigenvectors will be 1. So if we are multiplying by gamma, which itself is less than 1, then the eigenvalues will definitely be less than 1. So this is also true. And for this same gamma, the sequence defined by Vn is equals to R pi plus gamma times P pi of Vn minus 1 is a Cauchy sequence. So this is what we are basically doing. We are simply applying the L pi operator on the previous value of Vn at n minus 1 time step, and then we are getting it to at nth step. So this is the Cauchy sequence. This was also discussed in class. So whoever has like followed the lectures can simply get these answers. And it is a Cauchy sequence using the max norm. So max norm is this norm which basically returns the max of all the components. Suppose if x is a vector and its dimension is d. So whatever like capital D. So if we take d is equals to 1 to whatever is the maximum dimension, and that to absolute value, it was that's the absolute value. So this is also true, right? So the true options are all the three, and this is the correct answer, right? If there is any doubt, you can ask me now. Otherwise, like I'll move to the next one. Okay, so this is again a simple question. Select the correct Wellman optimality equation. So again, like we can reject it. Simply other options which are wrong. So gamma, either way, like it shouldn't be here. So this is definitely not the answer. Again, gamma, it's not here. Definitely not the answer. And this also like this reward is missing here, right? So this is also not the answer. This is the correct Wellman optimality equation, like max over actions, then summation over like this, all the other states which we can transition to. This includes the state itself because sometimes we have self loop. So we can go to that state also. So these are the like probability if we are in state S and we take the action A, what is the probability that we go to some state S dash? And once we go to that state S dash, that like what is the reward we get in expectation n plus gamma times value of that S dash. So this is dash. It's not visible. So okay, this is the third question. This is also quite simple one. So now I'll move to the fourth question. So fourth question says in MDP, there is a unique resultant state for any state action pair. And so suppose if we are in some state S, we take some action A, but it's not guaranteed that we will land in the same state. Like with if our policy pi is stochastic, then it will map the state to a probability distribution, right, over actions. So in that case, like we are not sure, like we can take the action, but the issue is like we might not land in the state which we like. We might not land in a unique state because that is like kind of determined by the environment dynamics. So our job is to simply take the action, whether it's stochastic policy or it's like even a deterministic policy. Once we take the action, but we cannot be guaranteed that we will end in that state, because it will be determined by the transition matrix, and like it kind of depends on the stochasticity. If stochasticity is there, then we are not, we don't know where to land. So definitely like this is false, because like we cannot be sure that we will land in only one state, right? Again, if there is any doubt in this, you can ask me. Otherwise, I'll move to the next one. So the next one is for an operator L, let x be one of the fixed points. So this is given, x is a fixed point. Now consider the following points. So what is the like property of a fixed point? So for an operator L, so basically like if we apply this L operator, then it gives L. And this we can do any number of times. So either way, like L, you can apply it m times or n times, both will be equal to x. So it will be definitely 2, right? We have to give that 2. And we can apply it 2 times also, then also result will be same. So the answer is 1 and 2. So both are correct. And you can apply any times, like this is a fixed point. So the property of fixed point is that you can apply this operator any number of times, the answer will still remain the same. So you, this n can be any natural number. Okay, if there is any doubt in this section, you can ask me now. Otherwise, like I'll move to problem solving. Okay, then I'll move to problem solving. So like this problem is kind of, you have to read the paragraph and kind of formulate the MDP. And the answer which you need to give is like which of the following are valid transitions of that MDP. So let's read it. Some time ago. So like basically like you have received this letter. So dear friends, some time ago I bought this old house, but it was haunted by a ghostly sardonic laughter. So basically like this guy purchased the house and there is some ghostly laughing in that house, and as a result, it is hardly habitable. There is hope, however, for by actual testing, I have found that this haunting is subject to certain laws, obscure but infallible, and that laughter can be affected by my playing the organ or burning incense. So organ is a like musical device, and burning incense, like we call agarbatti, like we burn it during holy practices. So in each minute, the laughter occurs or not. It shows no degree. What it will do in during the ensuing minute depends in the following exact way on what has been happening during the preceding minute. So there is some kind of temporal dependence. So basically like the next state will be determined by what has happened in the previous state. So suppose when there is laughter, it will continue in the succeeding minute unless I play the organ, in which case it will stop. So basically like if the like one state can be L state, laughter state, it will go to maybe quiet state only when you play the organ. If you like it will continue in the succeeding minute. Otherwise, like if you don't play organ, like it will kind of continue. So there is some kind of self loop here. But continuing to play the organ does not keep the house quiet. So once you have reached a quiet state, if you again play the organ, then like you might come back to laughing state. So it doesn't keep the house quiet for long. But however, another thing to note is that when this person burns incense stick, when the house is quiet, suppose you are in the quiet state and this person burns incense stick and does not play the organ. So it's like his action will be burning incense stick, and so this is like end operator, and like he is, this is not operator. He is not kind of playing organ, maybe denoted by O. So in this case, like it will remain in quiet state. And as this minute of writing, the laughter is going on. So please tell me what manipulations of incense and organ I should make to get that house quiet and to keep it so. So basically, like this person has written you a letter. He is asking you for help. Okay. Is there anything like which you didn't understand in this problem? Otherwise, like I'll move to the actual description. So assume that we make the following decisions in formulating this problem as an MDP. So the state set is again L and Q. So there are two states. L indicates that there is laughter and Q indicates that the room is quiet. And the actions that will be a combination of either you can play organ and burn incense, play organ but do not burn incense, do not play organ but burn incense stick, and do not play organ and neither like you play the organ nor you burn the incense stick. So these are like four actions for you. So O corresponds to playing the organ. So this is like the not operator. You might have studied in Boolean algebra, and this is the AND operator. And this is all, although it's not there. So okay, so this is there. So we consider this as a continuing discounted problem with gamma is equals to 0.9. So this is the discount factor and we let the reward be +1. So the reward is +1 for any transition into the silent state. So whenever like we are moving to this quiet state, regardless of where we are coming from, we can either come from laughter state to here, or we can move from quiet state to here also. So in both the cases, reward will be +1 and -1 on any transition into the laughing state. So like if we are moving from quiet state to laughter state, then it will be -1, or we are continuing in the laughter state. So again, like the void will be -1 in this case. So like the first task is to like basically kind of formulate the MDP. So the question which is asked here is like assuming deterministic state transition. So one thing to note is like the our policy is deterministic and rewards based on current state and action, which of the following four tuples. So basically like they have given us like 8 options and we have to point out which of the them is correct transition. So the tuple is like current state, then action you take, next state you land in, and the reward. So this is the tuple. So first, like we will kind of formulate the MDP, right? Once we formulate the MDP, then it will be quite easy for us to know which transition is correct and which is not. So let's formulate the complete MDP. So, so we are in like laughter state. If we are in laughter state, then if you play organ, then you will definitely land in a, a quiet state, right? You can do this. So quiet state, you will be having +1 reward, and you can land in this quiet state even by without burning the incense stick, because the requirement is only that you need to play the organ, then you will move from laughter to quiet state, right? So again +1. Now if you are in laughter state and you don't play organ, so there was an unless written. So if that thing is there, then if you don't play organ, then you will remain here, right? And once you remain here, so any transition into L means -1 reward. And again, like the second one will be you don't play organ, right? And you don't burn incense stick also, then also you will remain here. So the only way you can move from laughter state to quiet state is by playing the organ. And incense stick you can burn, like regardless of whether you burn the incense stick or don't burn, you will land in this quiet state. The only thing that matters is you need to play the organ, right? Now, once we are in the quiet state, now we need to see what we have to do. So in quiet state, it was mentioned that if you don't play organ, right, minus organ, and you burn the incense stick, then you will remain in quiet state. But as soon as you like play the organ, then you will definitely land in laughter state. So it's like you play an organ, and this happens regardless of whether you burn the incense stick or not. So again, like this will be even if you burn the incense stick, still you will land in laughter state if you are playing organ, and the same for like not burning the incense stick. So the last action which is remaining for this one is you don't play organ and don't burn incense stick. So in that case also it will be in laughter, because it is mentioned in the questions like here. Like if you are in the quiet state, then you have to burn the incense stick and do not play the organ. Then only it will remain quiet for the next minute. Otherwise, like it will move to laughter state. So using this, you can get this last transition also. So like let's write the action. and again the reward will be -1. So we basically just have to mention which of the following are correct. So if we are like in laughter state and we are taking action, playing organ and incense state. So this is the action. Then we are landing in quiet state and getting the reward +1. So is this true? Yes, this is true. So if we are in laughter state and we are taking the playing organ and not burning incense stick, then do we remain in laughter state? No, we go to the quiet state and we incur the reward of +1. So this is wrong. Again, so in we are in laughter state and we take action, not organ, but incense stick. So, but this says that you go to Q, but you remain in L. So this is also incorrect. So the D option is you are in the after state, and this action it is asking neither playing organ nor burning incense stick, and you remain in laughter state and you get a reward of -1. So this is correct option. So actually, like these kind of problems may be there in your exams because like these are something which happen in real world. Although like this example is like related to ghost and all, but there are problems where real world situations have to be formulated as an MDP, and this is a like challenging task. So like uh, there might be a question like this. So now like remaining four transitions are with respect to the quiet state. So when you are in quiet state, so okay, quiet state, and you play organ and you burn incense also. So this is the action which we are talking about. Then you remain in quiet state. No, we move to laughter state. So this is also wrong, right? So the remaining options are like, so you are in Q state and you play organ and then you play organ and do not burn the incense stick. Then you go to laughter and -1. So this is correct, right? And in Q state, okay, so you take not play organ and you burn incense, then you will remain in quiet state with the reward of +1. So this is also correct. And the last one is you are in Q state. So this is the action it is talking about. You don't play organ and don't burn incense. Then you move to laughter state with a reward of -1. Okay, so these are the options, correct options. So I hope like everyone understood this kind of problem because like not just related to exams because if you are pursuing a career in reinforcement learning, you in real life applications you will have to formulate that MDP. And sir also discussed some like problems related to New Zealand farmers and all in the lectures, right? So all those kind of problems happen in real world and you have to like reduce it into an MDP. Once you have reduced it into an MDP, then like you can apply these algorithms, right? Like I'm talking about planning algorithms. Learning algorithms do not need this kind of abstraction. So now the second question, again, it's related to the same question. So based on the above problem description, so the letter you received, he was asking for your advice, right? So what advice will you give? So this is the name of the person. So it was there at the end. Slightly awkward name. So what is the advice you'll give? If there is laughter, play the organ. Okay, so this is right, like first part. And do not burn incense if the room is quiet. So if the room is quiet, you have to burn the incense, right? Play the okay. So this is related to if you are in laughter state. So laughter state basically says that play the organ and do not burn incense. But you can like burn the incense also and like you can land in quiet state. So this is partly correct. And if the room is quiet, play the organ. So if the room is quiet, we don't play the organ, right? We have to not play the organ and burn the incense. So this option is incorrect. Never play the organ. So never play the organ, always burn the incense. But if you are in laughing state, you don't play the organ, you will remain in laughing state only. So again, like this is also incorrect. So this is always play the organ, never burn incense. So again, like if you never burn the incense stick, then how will you, if you are in quiet state, then how will you keep remaining in quiet? Okay, so the goal of this problem is to like remain in quiet state, right? Because like laughter, no one wants. So again, like if you don't burn the incense, then how will you keep on being in the quiet state once you have reached it? So again, this is also wrong. And if there is laughter, play the organ. right? So if there is laughter, so when laughter was there, only requirement was you need to play the organ. You can burn the incense stick or you cannot burn the incense stick also. So both cases you were landing in quiet state. And if the room is quiet, do not play the organ and burn incense. So if the room is quiet, do not play the organ and burn incense. So this is also correct. So this is the advice which we should be giving to that person. And like this is like this we have got a qualitative answer after like formulating it as an MDP and then like kind of seeing like what should be the ideal strategy, because the goal is to remain in this quiet state. If you are in laughter state, then go to quiet state and then keep on being in quiet state. So that is the, I hope like there is no doubt in these two questions. If there is, you can ask in chat. Maybe I'll check chat once. Okay, so someone is asking the reference book for this content is certain book. Do I need to refer to the second edition or first edition is also required? I think like second edition is fine. First edition is slightly old, but like since professor has like kind of read that edition, so sometimes he might refer to it. But generally, like many people like kind of prefer the second edition. Okay, then I'll move to the next question. So the next question says, if a policy is greedy with respect to its value function, then it is an optimal policy. Like basically it kind of means that if you are being greedy with respect to own value function, so we are kind of maximizing the value function, then like we will be having the optimal policy, right? Although like same optimal value function is unique, right? But it can map to multiple optimal policies. So multiple optimal policies can be there. Suppose pi 1 star, pi 2 star, pi 3 star, but all will map to the same value function. So if we are being greedy with respect to the value function, then it will definitely result in an optimal policy. So this is true. Is there any doubt in this? I hope not. So now I'll move to the next question. So again, like a problem kind of question. So consider a 4 by 4 grid world problem where the goal is to reach either the top left corner, so top left, or the bottom right corner. Okay, so this is the goal. The agent can choose from two actions, up, down, left, and right. Okay, so it cannot move diagonally. So that is not allowed here. And which deterministically, obviously, like if you move, go up from here, then you will deterministically go up and cause the corresponding transition and except that actions that would take the agent of the grid leave the state unchanged. So suppose if you are in then this state and you want to go up, then like you will keep remaining in this state. So you cannot leave the grid. So that condition is also there, and same applies here. You cannot go further left from here, further down from these four states, and further right from these. So we model this as an undiscounted. So undiscounted means gamma equals to 1. Because like we are multiplying by gamma, gamma square. So essentially we are multiplying by 1, and multiplication by 1 like it causes no issue, right? So where the reward for is -1 for all transitions. So this is also important. So reward is -1 means like the agent should try to like reach the goal state as soon as possible, because otherwise if it keeps wandering in this grid, then it will kind of keep on suffering these -1 many times. So the goal of the agent should be like to reach the goal state as soon as possible to avoid these -1s, right? Even though like there is no positive reward for reaching the goal state, still that negative rewards drives it to reach the goal state, because once it reaches the goal state, then the problem ends. So suppose that the agent follows a equiprobable random policy. So equiprobable random policy means like all the actions are equiprobable. So maybe probability of uh, you can say probability of down is 1 by 4, 0.25 basically. And similarly for up, right, and left. So all these are 0.25. So given below is the partial value function for this problem. So in this problem, like they have given the partial value function, like so basically what is a value function? Value function maps each state to a real number, right? So these are the states for us. Each cell is a state. So there are 16 states. So for some of the states, they have given us the value function, and you can notice like most of them are negative, right? And because like the reward itself is -1, but these are the goal states. So if you are already in the goal state, then you'll like are already in the goal. So there it's 0. And so what we have to do is calculate the respectively the missing values in the first and second row. So first, so this one you have to calculate, and this one you have to calculate the value. So let's do it, right? And they have given options also. So we just have to see. See, if like they didn't give us these other values of the other states, then it will be like we will have 16 equation, right? And 16 variables. Then solving this manually would be very hard, right? You can use some like solver, but this is from the perspective of exam. So they have given you some values of some of the states, and using that, like you can like kind of derive the values of these. So basically, like if you are in this state, right? So you will need value of this state because you can move from this to this state, and this state also. So and if you go try to go above, then you will stay in the same state. And similarly, like for the all the surrounding states where you can move, you have been given values. So let's start. So what is the like formula of V pi, right? So although like the formula includes a component of sigma action, and there will be a probability of A upon S, right? A given S. But this component won't be there. Do you know why? Because the policy which we are following is deterministic policy. So like we don't need to have this component, because like it will be like if you are in a certain state, you will only follow one particular action, not a probability distribution over all the actions. So like this has been given to us, right? Here they have mentioned that you are following deterministic kind of policy. Now what we have to do is now the second component comes like this comes over sum of states, like the states where we can go from this state. So this is the state. These are those states, and there will be a certain probability that with what probability we will go. And since like another assumption is like that it's equiprobable. So we will have that also. And now what we need to do is we have this r plus v pi of s dash. So this is the like basically the formula. So we just need to like plug in the states and see like what happens. So let's do it. So like probability 0.25. So this will be like same for all the four states, right? 0.25, 0.25, and 0.25. And we will be adding this. So this is due to the sigma, right? Now, if we are moving to state like, suppose we are, and what is the reward? So reward is -1 for all. So -1, we can have -1 here, again -1 here, -1 here. Now what we have to plus is again like what is gamma? So it's undiscounted. So gamma is 1. So we can like kind of remove it from the equation itself. Now what we have to do is like where we can move. So let's see. So we are in this state, right? So first we are calculating for this one. You can go like first we calculate for up. If you go up, then you will eventually land up in this state only. So it will be, and this is equal to, we are calculating V pi of S. So if you remain in that state, it will remain V pi of S itself. Now let's see where we can go. If we go down, then we go in this state. So its value is -18. So plus -18. Now, if we go left from this state, then we are getting 0 value. So for this state, it's 0. right? And if we go right, then we are getting minus 20. So it's minus 20. So you just have to like kind of solve this equation. So this 0.25, you can write it as 1 by 4, right? So that gets cross multiplied here. So v pi of s is equals to, and this entire summation. So minus 1 sum to minus 4, right? And plus v pi of s, and you can sum these minus 38, right? And this like gets cut. So 3. So 3 v pi of s is equals to minus 42. Imply v pi of s is equals to minus 14, right? So this is the value. So these options you can reject. So minus 14 is the value. So this state will have minus 14. And in a similar way, we have to calculate the value for this one. So I hope like there is no doubt in this. If there is, then you can ask me now. So these kind of calculations will definitely be there in your exams. Now let's do for second one. Okay, so same kind of scenario here again. So v pi of s is equals to 0.25, 0.25, 0.25. This is because like we are considering equiprobable. Again, like the reward will be minus 1 in each, right? Now let's see. So if we are in this state and if we move up, then we get like value of this state will be minus 22. So it will be minus 22. And again, the discount factor is 1, so we have kind of ignored it. Then we go down. So if we go down, then we get minus 14. So okay, so minus 14 here. Then we go left. Left we get minus 20. And when we go right, right, we will remain in this state. So it will be that value itself. So minus v pi of x. So again, like we perform the same calculation. So this will be 4 v pi of s is equals to, this will sum to minus 4, and this will sum to 22, 36, 56, minus 56, and this will sum to, this will be simply, oh, it will be plus, right? Because the default is plus, right? This is minus came because like it was minus, the value itself was negative. So plus v pi of s. And again, like same, this will be 3, so 60. So v pi of s will be minus 20. So this one is minus 20. So once we have minus 20, so this is the answer, right? V1. So if there is any doubt in this one, you can ask me now. Otherwise, like I'll move to the next question. Okay, so like same, like related, it is also related to the same question. If pi is equiprobable random policy, what are the respective values of q pi of s1 down and q pi of s2 down? And what is s1 and s2? S1 is the last cell in the third row. Okay, S1, last cell in the third row. So this is S1, and S2 is the last cell in the second row. Okay, so S2 we just calculated. So for these two cells, it's asking. So what is the formula of this Q value? So you can know that Q pi of S1 down. So first we are considering this one. And this can be written as summation over S dash all the states. Suppose if we are in this state, then why taking down action? Like which action, which states we can go in. So this is like just one, right? We don't have to move to many states. So either way, like for the sake of equation, I'll write it as dash S and down. This is the probability, and you'll get some reward. Reward as usual, it's is minus 1 for all the transition plus v pi of state that you land in. But since like once we are in that state, we go down, we will land in only one state. So this summation will be over only just one state. So it will be like one probability here and minus one reward. Now let's see what happens when we go down from there. When we go down from S1 state, we go to zero value. So plus zero. So like it's minus one only. So, although like you can reject all the other options, but still like just for the sake of it, we can do the second one also. So second one in a similar manner, like it's is also asking for down state, right? So for down action. So once we take down action, we can only land in one state. And in doing so, again, like it's we get to a state. So this is S2, we move to minus 14 value state. So it will be like similar kind of calculation, but here it will be my plus like minus 14 plus minus 14. So once we add it, we will get minus 50. So this is the correct answer, right? So these either like one problem which they can give an exam instead of giving like you 16 state problem, they can give you a like 3 state MDP and ask you like to solve like you can solve three variable three equations. So either they can ask that, or like if it's large, then they will give you like value of other states and then ask you to get the value of some missing state. And similarly, like you need to calculate those Q values also. So you need to like have these formulas in mind. Okay, so now we move to the sixth question. So the sixth question says in a particular grid world example, reward are positive for goals. Okay, negative for running into the edge of the world. So edge of the world basically means like if we are here, like if we go up, we are into edge of the world. So like grid is our world, the grid world. So we if we go in edge, then we get some negative kind of reward and zero for all other transitions. So there might be some goals there. Are the signs of these rewards important or only the intervals between them? So they are asking us to prove something. Prove using the discounting return equation that adding a constant c to all the rewards add a constant k. So if like this reward will be like plus something c plus something c, and again like all the rewards have plus c something, then like the overall the reward will be like kind of increased by some constant factor k, and they are asking us what is the value of k. So okay, so let's see like in this equation what is happening. So if we add plus c to first one, then we get c extra, then we get gamma c, right? Because like gamma into this plus c. So gamma c, then again here it will be gamma square into c, right? This is the extra thing, and so on. And this is carrying on till infinity, right? So again, like we take c common, and this is 1 plus gamma square plus dot 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 dot. And this is what is called infinite GP. And as usual, we know that gamma has to be less than 1 because it is a discount factor. So it satisfies that assumption of infinite GP also. So the sum of an infinite GP is like first term upon 1 minus common ratio, right? So in this case, it will be, so the C will remain. So first term is 1 upon common ratio is gamma. So basically like this is the value of k. K is equals to C upon 1 minus gamma. So this is the answer. Okay, so if there is any doubt in this, you can ask me. Maybe I'll check chat once. So I think there is something. Okay. Yeah, good that you are getting this. Now I'll move to next question. So this question is slightly reading based. So given an algorithm reinforcement learning problem, algorithm A will return optimal state value function. So yeah, like this V star, like uh, generally we call it value function, but since this Q function, like it's called action value function. So sometimes what happens is like this. some people call it state value function so as to differentiate. But by default, if it's just within value function, then it will refer to V function. So sometimes like some of the literature call this V function as state value. So basically like A is returning us algorithm A is there. It's giving us V star, optimal state value function for the problem. And algorithm B returns us optimal action value function. So V algorithm is given us Q star. Your aim is to use the value function so obtained to behave optimally in the environment. Okay. So we basically want to extract policy pi because policy pi kind of decides like whether we are some mapping from state to action or some probability distribution of action. So this decides our behavior. So assuming that you know the expected rewards, so we don't know the transition probabilities. Okay, we know the expected rewards corresponding to the problem in the question. Which algorithm would you prefer to use for your control task? So basically, like the problem reduces to that from which of these function, like V star and Q star, it's easier to extract the policy I star. So let's see this. So like once we have Q star function, right? Q star function, what it would be like. So suppose if we have a table, here we have written S1, S2 and all those states and A1, A2, all those columns are there. So there will be a cell. So for each action, there will be a Q value, right? Like, so this will be like Q function is like function of state also action also. So this cell will corresponding to one state and one particular action. So now what they are asking is, can we like simply obtain the like, and similarly like for value function, it will be like just one column, right? So value function doesn't depend on state. So value function is like just the function of state. So one particular value. So it's like uh, a vector for value function, and it would be a matrix for this Q action value function. So now from which of these like is it easier to extract the policy pi? So like once we know we are in some state, right? We need to decide on which action to take. So we can simply take an argmax over all the action, right? And we can get like whichever action is returning us the maximum Q value. So from that, like if we take argmax, suppose like pi of S equals to argmax over action A and whatever Q star of SA is there, right? So like once we have the optimal Q value function, we can get the optimal policy simply by taking the argmax over action space. And one thing to note is that this argmax might return many actions because it might happen that more than one action might have the same Q value, right? So it might return those actions. So there might be more than one optimal policy, but either one of them is fine for us. As we will see in one of the demo also today, so like this algorithm V is the answer because from algorithm V, we can easily extract it just by argmax. But for value function, you'll actually need these transition probabilities because like if you write the formula like how to extract policy pi from a value function pi, you will need those probabilities also. So for value function, we cannot extract, but for from action value function, we can simply extract. And here, like the action value function is given in terms of value, like this table is given to us. So we can simply take the arguments. Okay, then like moving to the next question. So in proving that L pi is the contraction, so this was from the proof, we had this expression. Okay, so it's like summation over gamma. So gamma is common on both sides. Okay, so basically sigma over J, probability of landing in J state from S state, and Vj minus Uj. So we were considering two value functions there. And this equation has been like, this equation shows up in the proof. So the question they are asking is like this inequality holds because why does this inequality hold? So suppose maybe I'll give you an example. So this will help you understand better. So suppose we have vector 2, 4, and 3, and we subtract vector 1, 5, and 1, right? So what we will get is 1 minus 1 and 2. If we take the max of this, right? Max norm. So we will get 2, right? Max norm. And if we take the differences of this one, it will be like, uh, so what I'm trying to say is like if you are distributing some probability mass. So here what we are doing is we are giving some probability to like this one, maybe 0.25, 0.25 again to this -1 also, and maybe zero point 0.5, whatever probability. So this is happening here. So this sum, like 0.25 multiplied by 1, 0.25 multiplied by -1.5 multiplied by 2. Or one thing we can do is on right hand side, what we are doing is we are allocating the complete probability to just this 2. So this will always be greater than this. So you might have studied in physics like moments. So if we have to like assign probability and we have to like some probability is there and some values are there, p1, x1, p2, x2 plus. Suppose p and xn is there. Then if you want to maximize this equation, then you should assign complete probability to the element which is maximum among them. Then only you can maximize. Otherwise, like this, probability is getting distributed over suboptimal elements. So that way, like we cannot get max. So this is the reason why like this inequality holds. So the options they have given is Bj minus Uj is a component of this. It cannot be a component. This thing is a scalar. So this is wrong. The maximum of the difference on the LHS is less than the maximum of the difference. Uh, no, this is also wrong. The difference in LHS can be negative, but the norm in the RHS is non-negative. Like this statement is true, but like this is not the reason why this inequality holds. So this is also incorrect. But this is like the max norm on the RHS can at worst be equal to the difference in the LHS. And when this will happen, suppose if all the elements are equal, right? Then you can assign the probability in whatever way you want. So that is a possibility. So at worst it can be equal, but it will never exceed it. So this equality also comes. So this is the reason. I hope like you got it. Okay, so like let's move to the ninth question then. So we define the operator L pi. So this operator L pi was defined as V mapping from like this value function to value function, and this is in the vector space. And this is how we defined it. Having seen the proof of the Banach fixed point theorem, assuming that like these are the usual notations, which among the following are implications of showing that L pi is a contraction. So like suppose we have shown that L pi is indeed a contraction mapping. So what does this fact implies? Does this imply that V pi is a fixed point of L pi? Like this statement is true, but like this is not the implication of Banach fixed point theorem, right? So like what it implies is that it has to be unique. So this is the correct one. And if we repeatedly apply L pi starting with arbitrary V resulting in convergence to V pi. Okay. So if we can keep on applying this L pi, then we definitely go to V pi. And same statement, but we go to V star. No, we don't go to V star. So I think in the week 5, you will be told how to reach this V star. And that is not by applying L pi, but L pi is Bellman operator. And there's another operator which is called Bellman optimality operator. So once you keep on applying this Bellman optimality operator, then you reach this V star. But if you simply apply Bellman operator, then you will reach V pi only. So option D is incorrect. Although like option A is like true, it's not false, but it is not the implication of this fact that L pi is a contraction mapping. So this contraction mapping like kind of implied that this unique that fixed point will be unique because this is one of the point of the Monad fixed point. You know, it was not to show that there is a fixed point exists. it was to show that that fixed point is unique, right? Okay, so if there is any doubt, you can ask me. I'll check chat once. Okay, so then I'll move to the next question. So this is like given a value v. Okay, so this is like v is the vector space. So we are given one specific value function. And suppose L pi of v is equal to v dash. So we have applied this contraction mapping L pi on this point v, and it gave us v dash. Can we conclude that v equal to v dash? We cannot say that, right? Because like it, it will happen like like v, if it's a fixed point, then it will result in v. But we don't know this v dash. Is it equal? It could be something other than v also, right? So this is not possible. And v is not equal to v pi, v dash. This also we cannot say because it might happen that this v is the fixed point and v dash can be equal to v. But what we can say is that L pi we know is like a contraction mapping. So what is the definition of the contraction mapping? Like suppose V and V dash are 2 points. These could be same or different. But once we apply that contraction mapping, then like this will reduce the like this is the original distance between V and V dash, and this is the like distance after applying that contraction. So that this is measured by some norm, and that like distance decreases. That's why this is a contraction mapping. So this is something which we can say, but we cannot say this v equal to v dash, or we cannot say both of them because this could happen and this could happen too. So we cannot conclude that. So this is not a definite conclusion. Might happen, might not. Again, this might happen, might not. So, but this will definitely hold. So this is the correct answer. Okay, then I'll move to the next one. So which of the following statements are true for a finite MDP? So we need to see like which of the following are true. And the MDP is finite. So the Bellman equation of a value function of a finite MDP defines a contraction in Banach space. Yeah, so we were working in Banach space only. And the norm which we used was max norm. And that value function like Bellman equation, it kind of defined the contraction like it was L by, right? Now, if gamma is like less than 1, the usual value of gamma, then the eigenvalues of gamma p pi are less than 1. Yeah, like this we saw in one of the previous question also, because like p pi, like the maximum eigenvalue will be 1. So max of E1, E2, all those E, suppose if k eigenvalues are there, it will be 1. So if we are multiplying by gamma less than 1, then it should be less than. So this is also true. Upper one is also true. The Bellman equation of a finite MDP can be solved. So here it's asking about Bellman equation, not Bellman optimality equation. So we saw a question about Bellman optimality equation. There it was false, but here since it's asking about just the Bellman equation, so it can be like solved using linear system of equation. So like that there will be, suppose if this is the number of states, so these many equations will be there and these many variables also. So we can solve it. Yeah, this is also true. So the sequence defined by like this is our, so basically like we are applying the L pi contraction operator is a Cauchy sequence in Banach space using the maximum, and p pi is the stochastic method. Also like this was proved in the convergence. So it turned out to be a Cauchy sequence. So this is also true. So all of them are true. So these are like simply like fact-based question asked from the lectures. Okay, then I'll move to the next one. So like in this, like they are asking what is true about the discount factor in reinforcement learning. Uh, so first option is discount factor can be any real number. No, it cannot be any real number. It has to be between 0 and 1. Can be 1 also in some cases, but like those are like where like we know like there are problems which are called finite horizon problems, where because where we know that it will definitely end in a finite number of steps. So in that those cases we can have gamma equal to 1, but we cannot have it as any real number. This is false. The value of gamma cannot affect the optimal policy. It can actually affect the optimal policy, right? So this is also false because like suppose if gamma is like near zero, maybe gamma equals to 0.1, then like you are kind of focusing on long-term rewards, right? But like no. So if gamma, maybe just take it gamma equal to zero. So what this means is like the reward was RT plus one plus like whatever like is getting multiplied by gamma in the future, like gamma square and all, like all that will go to zero, right? So it we are basically focusing on just one step reward. So in this way, like our behavior could be different according to gamma. But if we take gamma is equals to maybe zero point 0.9 something, then we are kind of prioritizing like long-term rewards. So not just the current reward, but also like suppose current reward was some RT plus one, then zero point 0.9 square, then zero point 0.9 in square and so on. So we are giving some weightage, although it's reducing getting discounted, but we are actually focusing on long-term rewards also, long-term stuff. But in this case, we are focusing just on the one-step reward. So what will happen? Suppose if we are in some state, some action is giving plus minus one, some is giving plus one, some is giving plus three. So instead of worrying what happens later, we are simply focused on getting this reward if we have gamma equal to zero. So in this way, like our like actual policy might vary according to gamma. So value of gamma can actually affect the optimal policy. Okay, so third option is actually what I have explained. The lower the value of gamma, the more myopic the agents are. So the agent basically maximizes the rewards that is receives over the shorter horizon. So suppose if gamma is equals to zero point 0.1, we are kind of moving towards the gamma equal to zero zone. So it's like we are focusing because this zero point 0.1 like squared will be 0.01, right? And then 0.001. But it's still like if we have zero point 0.9, it will be 0.81 more weight. Like compared to this, still 81 is more than just one. And then point maybe 729. So it's still more than this 0.00. So in this way, like it becomes myopic. So this is the correct option. I hope like there is no doubt in this one. So now the last question. And I think like a similar kind of question is there in assignment also. So maybe like I'll solve it here and you guys can solve the question in the assignment. So what is asked is consider an ambiguity with three states, okay, ABC. The state transition is defined as from each state. We can choose from two actions to go to one of the other two states. Okay, so self loop is not allowed here. So we can choose from two actions to go to one of the other. Like we don't stay in the same state. If we are in state A, then we can choose an action that takes us deterministically to either state B or C. So A to A is not allowed. And the rewards are given for each transition, like A to B, then B to A, B to C, C to B, A to C, and C to A also. And discount factor is zero point 0.9. So what they are asking is find the fixed point of the value function for the policy, and they have given us policy also. So if we are in state A, then we move to state B, and if we are in state B, we move to C, and if we are in state C, then we move to A. So this is the policy which we are given, and we have to find the fixed point. So like you might remember this equation, like this is called something. Can someone write in comment like what is the equation for fixed point is called? Like it has a like name. Maybe I'll wait a few seconds. It's not Bellman definitely. Like they like kind of derived the equation to get the fixed point. It was in terms of inverse of some matrix, you might remember. So it was actually called the green equation. So in fact, like one of the topics is named after this. So green equation. So what is green equation? So green equation says that the fixed point is basically this identity matrix minus gamma times this p pi inverse of this thing and multiply by rewards. Okay, so let's solve this. Okay, then so it will be identity matrix. So we are dealing with three state, right? So three state identity matrix 1 1 1 0 0 0 0 0 0. And what is this? Minus. And gamma is given to us as zero point 0.9. minus 0.9 times, and this is the stochastic matrix P pi, right? So P pi like first column corresponds to A. So from A we are going to B, right? From A we are going to B. So for B, like we will have 1, for others we will have 0. Because with certain probability we are going with to B, because this is what the policy says. If we are in A, we move to only B. And when we are in B, then we move to C. And when we are in C, we move to A and don't go to others. So this is the matrix for which like we need the inverse. And simultaneously, we will need rewards also, right? So let's take the reward. So what is the reward we get by moving from A to B? So A to B, we get -2. And B to C, where is B to C? B to C, we get 10. And C to A, we get 4. Okay, so this is the like our reward vector. So basically, like first we have to find the inverse of this one and then multiply by this, and this will give us the fixed point. Okay, so like let's do it. So this will be let's make it big. So 1 here, then it will be minus 0.9, then 0, and then 0 here, then this one, and minus 0.9. Then here it will be minus 0.9, it will be 0 here and 1 here. So we have to take inverse of it and then multiply by -2, 10 and 4. Okay, so you know how to calculate the inverse, right? You can take either the adjoint approach or you can take the Gauss-Jordan method of elimination. So either way, like I have used some online calculator, matrix calculator to calculate the inverse of this, and it comes out to be this nice value 3.69, 3.32, and 2.99, right? Then again 2.99, 3.69, and 3.32. You can see some symmetry, right? Some of the values are common. 3.32 and 2.99 and then 3.69. So this you have to multiply by -2, 10, and 4. So you know like how to multiply a matrix by vector. So this is like 3 by 3 and 3 by 1. So this entire row will get multiplied by this column. And in the same way, like you can multiply 3.69 by -2, 3.32 by 10, and 2.99 by 4, and sum them up. So it will give something like 37.8, 44.2, and 38.0. So this is the like the answer: 37.8, 44.2, and 38.0. So in a similar manner, like you can work out the example, which is actually part of the assignment also. So now like I'll move to demo, but before moving to demo, if there is any question you can ask in chat or just unmute yourself and ask. Otherwise, like I'll move to the demo. Okay, then maybe I'll start sharing the screen. So I hope you are able to see this screen. Can you like someone confirm in chat like you are able to see the collab? Yeah, okay. So you are able to see the collab. So maybe like I'll describe the problem first. So again, the problem is similar to what we have in the grid world problem. So suppose you are given this cell, maybe 3 by 3 cell, right? So you are in this corner, you are starting in this corner, and your goal is to reach this bottom right. You are in top left, the goal is to reach bottom right. But the special thing about this problem is like in the previous problem, like whatever we have seen till now, there was no restriction in any of the cell. But now maybe you cannot go to some of the cell has a barrier. So you cannot use that cell. So in that way, like you have to go this way. If like there is a barrier here also, then either way, like you cannot move diagonally. So you have the only way you can go is this way. So this is the problem setup. So now I'll start this. So again, like like this is built using simply the numpy. So goal is to reach the bottom right cell of the grid starting from top cell. But there are some barriers in some of the cells, so it might not always be possible to reach the goal. So you know this can happen. If suppose there are barriers here and here also, maybe here not, then you cannot reach because you cannot move diagonally. So in that case, like the reaching of goal is not possible. So there could be some cases like that. So you have to keep in mind. And basically, like what I am doing in this program is I am asking you to give the size of the matrix also, like size of the grid here. It was 3 by 3, but you can enter 5 by 5, 7 by 7, whatever. Like it's a square grid. So I'll ask you simply one dimension and the reward. So the reward here is +1 for reaching the goal and 0 otherwise. So, but discount factor is 0.9. So, you know, like this will kind of like make the agent go to the goal state as soon as possible, because otherwise, like if it waits for a long time, then this 10 will get diluted because that zero point 0.9 into zero point 0.9 will keep on multiplying. It will getting smaller. It will start getting smaller and smaller as we like delay it. So the goal of the agent is to like reach the goal state as soon as possible and collect this +10. And for all other transition, reward is 0. And like the same note that agent should try to reach the goal as soon as possible. Otherwise, like the overall reward will get diluted because of this gamma. If it was one, then it would be a different problem, because if it is one, then the agent can simply wander around and they will it might not be able to do it in the shortest path. It could, but it will not prioritize. So you have to set these factors. So basically, like in this program, you can set these discount factors. You can change these rewards also. I'll be sharing this file so you can play around with that. So this is the like maze solver class. So this is actually like solving. So the algorithm which I have used is like it's called value iteration. So basically, like this is not part of like week 4, but in week 5, some of the initial lecture is devoted to this value iteration. So I like before I mentioned this, right? And that if you keep on applying simply the Bellman operator, then you converge to BPI. But if you keep on applying Bellman optimality operator, then you converge to B star, like optimal value function. So we want to converge to this optimal value function. And value iteration simply like it starts with a random V naught and it keeps on applying this Bellman optimality operator on this. So we go to V1, V2, V3, and in same way, like once we reach a fixed point, then we will kind of stop because we have reached the optimal V star. So value iteration works in this way. So maybe if someone of you have started the lectures of week 5, then like it, you might understand this better. Either way, like the concept remains the same as Bellman operator. It's just that we are applying the Bellman optimality operator here. So next week, like I'll show demo policy iteration, but here like I'll show value iteration. So let's see. So enter the maze size. Let's enter 5, right? And also like the barrier probability, I'm getting it from you. So maybe like 0.1, like only 10% of the cells to be barrier. So, okay. So the agent has like kind of solved this problem. So this was the initial maze. So this is the start state. We are starting at top left and the goal is to reach this. So, but there is a barrier here. So one way which we can go is like we can simply go down and go here. But there are more than one way, right? You can go here, then go here, and then go. So like there could be multiple policies, but what I want to show you, like this is value iteration. So it is kind of applying this Bellman optimality operator multiple time iterate in an iterative manner until it reaches a fixed point. So once like these values stop changing, then like we have kind of converged. So in 22 iteration, like it has kind of reached a fixed point. So now we can see. So what is the path it chose? So it chose is like down, 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 right, 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 right. So this is the policy it came up with. And in just simply just 8 steps, we are able to reach the goal state. But one thing to remember is I have already discussed it, that we can do in multiple way, right? So suppose the first state we go here is value is 24, right? and second state is 27. So we can go to second state, which is 27 here, right? And then third state in this part is 30. So we go to 30 here, and then 33 here, then we can go to 33 here, then it goes to 37. So we move to this 37 here. Okay, 37 here. Then it moves to 42. So we move to 42 also. And it moves to 46. Now we are at the same point and we can move. So in this way, like there are two paths of reaching this, uh, like two shortest paths, right? Optimal, because we are doing it optimally. And other like option could be like there could be third also. If we like instead of moving here, we could have moved it here. So it would be 33, 33 here, then 37, 37 here, then 42. And now we take this one. Or we can like simply go down here, here, then here, here in this way. So there could be multiple policies, but the idea is like for all these policies, the value function is unique. So there could be multiple optimal policies, but the unique optimal value function, there is only one unique optimal value function. And second observation is length of the optimal path is 2 into mesh size minus 1. Because either way, like if you optimal means like you have to reach in shortest time, because otherwise that 10 is getting diluted, right? So you have to reach in the shortest time possible. So basically like you have to like move four is like this is the like 5 by 5 grid. So 4 steps downwards and 4 steps towards right. So it's getting multiplied 2 into mesh size minus 1. Like like you can do it in steps also, like first move 3, like 2 here, 1 down, then 2 down more. So in this way, but it's still like regardless, it remains the same. Like same number of, you have to make move the same number of steps down and same number of steps right. I hope like you got this. Maybe someone can write in chat. Otherwise, like I can show one more run of it. Okay, so maybe like I'll run it again. Let's see what happens if the probability is more. Maybe we take a small grid, 3, and this probability of error we keep it zero 0.9. So then what happens? So in this way, like we are kind of blocked, like the agent cannot do anything. So it brings too many barriers, solution does not exist. So maybe like I'll run it again one more time. This time I'll go for maybe 4, and let's see, barrier probability we increase it slightly, zero 0.2. Let's see what happens. So zero 0.2, what happened? So the barriers were here. So okay, so we can go first come here, then go here, then so there are multiple paths, or go here and here and here. But again, the same point remains that there could be multiple optimal paths. So what this agent picked up is down, down, right, right, down, right. But it could have gone down, down, right, 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 and then down. So either way, like both the values will be 46.67. And in a similar manner, it could have started instead of down, down, it could have gone to right first. So 30 here. So then down 33 here. Then it could either go 37. So either way, like it's 37 here, or it could have come on 37 itself. So the value function remains unique, but this policy might change. Optimal policies, like so basically like multiple optimal policies can map to the same value function. And like maybe you can play around, like I'll show you like where to play around. So this is where I'm setting the reward. So the goal reward is 10, and otherwise like the reward is 0 for everything else. So you can if you don't want discount, then what you can do is you can give some negative reward. If you have discount factor as 1, then you can give some negative reward so that agent has some kind of urgency. Otherwise, it won't have urgency if you have 0 reward and 1 discount, right? And in a similar manner, like you can set the discount factor also. Or maybe I'll show where I set the discount factor. So here, like by default, it's taking 0.9. But if you want, like you can set it to something else also and play around with this reward function, mesh size, probability of barriers, and also this discount factor. Okay, so I hope like you got this. So this is value iteration. Maybe like it's too early for you to like go through value iteration, but once you have like watch the lecture of value iteration, then definitely you will understand what is going on. So this is similar to Bellman kind of thing. Just that in that we were converging to BPI, but here we will actually converge to the optimal value function because we are applying Bellman optimality operator. Okay, then. So I'll go back to the slides now. Okay, so I hope the slides are visible. Maybe someone can confirm. Sure. Okay, so the slides are visible now. I'll move to the assignment 4. So as I mentioned before, also like this, like for this week, like in a way, like you have noticed also like the last last week's like week 4, almost like 6 sections were there. All were like theory heavy. So I also have to move to value iteration to show you a demo. Also, like these questions, there's not much formulation in assignment and practice assignment. So I try to give you like some problems like where which requires numerical calculations. You can practice these and some more practice problems from the book also. There are many problems in the book. But the thing with assignment and practice assignment is that you don't need to solve much. It's just theoretical kind of stuff. You just need to have watched the lectures and then you can simply do these questions very easily. So again, like the first question is the state transition graph for an MDP is directed acyclic graph. But like it need not be, right? Because like in MDP, we can have self transitions. So self transition, you can have cycles, or you can have this kind of thing also. Like you can transition to this state and then come back to this state. So we saw that ghost example, right? In that, like we were moving from laughing to quiet state and then quiet to laughing state also. So there was a cycle there. So it is directed definitely because there is an arrow, but it need not be acyclic. Cycles can be there. So this statement is false. Now we move to the question 2. So question 2 asks us like which of the following statements are true? Okay. So the optimal policy of an okay, so this is the assignment section. So I'm not supposed to give you the answer, but either way, like for first one, it wasn't that hard. Now I'll try to avoid that. So consider the following statements. The optimal policy of an MDP is unique. Like, does the optimal policy needs to be unique? So I showed you in demo also, right? It need not be because like there could be this value function needs to be unique, but there could be multiple. It could map to many optimal policies. So there could be many optimal policies, and this happens because of that argmax. That argmax can return many actions, right? So if argmax can return many actions, then it can like generate many policies. So like it need not be unique. So this is definitely false. We can determine an optimal policy for an MDP using only the optimal value function without accessing the MDP parameters. And the third option says we can determine an optimal policy for a given MDP using only, so this only is important and without accessing the MDP parameter. So we don't have access to probabilities. And because either way, reward we are getting from the environment, right? And state and action we always have. So maybe I'll tell you, like in RL, like initially we started off with mandates problem. So mandates are essentially one state MDP. So it's like you are in some state, you take an action, you come back to the same state. Again, you take some action, there could be multiple action, right? You can, but there's no more than one state. So sometimes these are called stateless MDPs also. So what we are currently doing is this is called as planning. So in planning, we kind of have access to these probabilities, transition probabilities. So you know the components of the matrix are set of state, set of action. Then there is a transition function. Sir writes it using P, but some literature writes it as T also. Then there is reward. So Sir writes it as an expectation something of R. So you can have that term. And the fifth is the discount factor. So in planning problem, we actually have access to transition function and reward function. Like when I say access, it means that we beforehand know that what is the probability of going from one state to another state by taking some action. So we know that probabilities in the beginning itself. So planning basically kind of reduces to computational problem. There's not learning happening. You saw those Bellman equation. So Bellman equations, we were simply like it's a set of linear equations. We were solving those equations. So there's no learning, right? It's just a set of equations. We are solving those equations and we are getting the answer, optimal policy. There's nothing learning. The agent doesn't learn anything. It's simply this is called planning. So methods like value iteration, which I showed, policy iteration, which will come later, and this can be done using linear programming also. So these three methods fall under the category of planning, where we have access to these probabilities. And third and the most important is the learning. And in learning, we don't have access to this T transition function. Reward we can get from uh, environment, right? You saw that structure in which like and suppose an agent is there and then environment is there, agent is taking action on this environment, and the environment comes up with the next state and reward. So reward you can learn by interaction and get it by from the environment by interacting with the environment, but these transitions we don't know. But there are some algorithms in which we can approximate these transitions by like we can like do it many times, like interaction with the environment, and see like if we are in some state, then we are landing in which state. So we can kind of approximate, but that exact number we don't know. So that thing is there. So the point here is like this is also similar to one of the question which we did, right? Where did it we do it? So yeah, this question we did, in which algorithm A has access to only the optimal value function, and algorithm B has access to optimal state action value function also. So, which was actually useful here. Like action value is basically useful. So from action value, we can easily extract the policy by simply by taking the arguments. So the statement here is we can determine an optimal policy using only the optimal value function without accessing the MDP parameters. This is not true, right? And but we can do so with the Q value function, optimal Q value function, just by taking arguments. Showed that table, right? You just have to take the arguments for a particular state, and you will get it can return one action or it can return multiple action, and that's why like we have multiple policies for the same optimal function. I think there is something in chat. Yeah. Okay. So this is done. Now I move to the third question. If there is any doubt, you can simply unmute or and ask or just write in chat. So which of the following is a benefit of using RL algorithm? So I mentioned this, right? Uh, RL algorithms actually fall in this learning category. And these are called planning algorithms, which like the phase we are in, like we are doing planning as of now. So these Bellman equation, Bellman optimality equation, and these methods like value equation. So basically what's happening is like Bellman equation, uh, you can solve to get V pi. But in order to get this V star, like you remember, like one of the question was also there. So Bellman equation you can solve as a set of linear equation. But this due to that max operator, right? This becomes set of non-linear equation. And solving set of non-linear equation is harder compared to solving linear equation. So for this reason, we employ these methods like value iteration, policy iteration, and linear programming. So these kind of helps us in solving this Bellman optimality equation and get to this optimal value function. So V pi we can get easily, but V star getting to that is relatively harder. We cannot simply solve linear equation because it's non-linear inherently. So we rely on these methods. So all this is called planning algorithms. So these are the planning algorithms. So this question, next question is asking related to RL algorithms. So which of the following is the benefit of using RL algorithms for solving MDPs? So RL algorithms, they do not require state of the agent. Like state is either way required, right? RL algorithms also, I showed that diagram. There is an agent, there is an environment. It is taking actions, it is getting state and reward, right? And this is happening over time and time. So this loop keeps on repeating. So they require state. So this is false. And they do not require the action taken by the agent for solving an MTP. This is also false flag because action is required, state is required. They do not require the state transition probability matrix. So that transition probability matrix is not needed. So this is fair. Like, but in planning algorithms, we need this T. Need T. So they do not require, and they do not require the reward signal. We require reward signal, right? We have to require reward signal because reward signal is our feedback from the environment that we are doing something right or wrong. If a children is like touches some fire, then he will get one. So he get a negative reward. That is the feedback. So from that, he learns that in future he will not try to touch the fire. But if he like drinks milk, then he feels happy. So he gets some positive rewards. So he will kind of, maybe if he finds a glass of milk, then he will try to drink it. So in this way, like reward acts as the feedback. So, but reward is needed, right? So this statement is also false. So which of the following is the benefit? Like, so RL algorithm doesn't require this transition probability matrix dependence, but planning requires. So here the question is about RL algorithm. So there that dependence is not needed. So this is actually a benefit of RL algorithms. But like one more thing to point out is that planning algorithms are simply like computational problems. So the agent is not learning anything. It's simply solving set of equations. Even these value iteration and policy iteration, these are iterative methods. So it's not learning anything. But RL algorithms, since they learn, there will be a phase in which when they are learning about the environment, in that phase, like they might not behave optimally. You remember that bandit thing in which like there was regret. So initially they were learning, then they kind of reach some optimal thing. So this phenomena happens in RL algorithms also. So this is like exploration, exploitation thing. All this comes in learning phase. So that is there. Now, like the fourth question, if there is any doubt in all this, like you can ask in chat. Okay, so there's no doubt. So I'll move to the next question. So next question says consider the following equation. So we are given few equations and they are asking which of the following is correct equation. So correct equation. So V pi of S is equals to summation over actions, probability of taking that actions and Q pi of S. Right? This is correct. Uh, like this is actually one of the way to obtain the value function, right? If you have q value functions, so I showed that table like uh q value function, you will have s1 s2 s3 and so on, a1 a2 a3, but for value function you will have simply just one vector. So what you do is like whatever is the probability of, suppose you are in state s1, what is the probability that you take action a1 in s1, and corresponding like that q value, you will multiply by that probability. And similar way, like you will calculate this probability sum. So that probability sum is actually equal to this, the value which is residing in this value function. So you can think some kind of weighted average over those actions. So this is the value function. So this equation is correct. Now the second equation says q pi of SA is equals to like this, this they have simply flipped and this probability has changed. So summation over states, but that reward thing is missing, right? This is not simply this. This should be some like if I denote that expectation by simply by R plus some gamma times this B pi of S dash, right? Then it's fine. But this is wrong. And the value function, what is value function? So this summation basically means that if let's take like we put I equals to t. So if we put t, then this becomes 0. So our I equals to t become t plus t. We are in some state s, and then like this is getting discounted, right? Gamma comes on, then we move to t plus 1, t plus 1 minus 1, and then it will be and like rt here, then it will be rt plus 1 here, right? Uh, Wait a minute. What is this? I plus t. This There's something wrong with this one. It should be just I, right? T plus, yeah, it should have been just I. Maybe this is one. So you are in IT, then you get gamma RT plus 1, then you get gamma square RT plus 2, and so on. And this is conditioned on that you are initially in that status, right, for which you are calculating the value function. So this is also correct definition. This is actually the definition of the value function. And in a similar manner, like you can get the definition of SA also. Like this is expectation, but the thing is like here, like your first action will be A. So like you need to find out which of the following are correct. Two is definitely incorrect. So I hope like there is no doubt in all this. Then I'll move to the next question. So again, like as I mentioned already, that most of these questions are simply theoretical. So state true or false. While solving MDPs, in case of discounted rewards, the discount factor cannot affect the optimal policy. We saw one question like this, right? Where was it? Like there, yeah. What is true about the discount factor? So the value of discount factor cannot affect the optimal policy. So same kind of reasoning here. It can actually affect, right? If like we have gamma equal to 0, then we are focusing on just one step reward. If we have gamma more, like maybe 0.999 something, then we give more weightage to the future rewards. You saw it here also. Like when we had discount factor 0.1, then this is getting multiplied by these factors 0.01 and 0.001. But here in case of zero point 0.9, it's getting first one is gets multiplied by zero point 0.9, then 0.81, then 0.729. It's still like much bigger. So this one is almost 81 times, 80 factor of 81. And this is even bigger, 729 factor. So in this way, like relatively, you can say that you are prioritizing the long-term rewards with a higher gamma. So this like kind of changes the behavior, like the policy which we obtain. So that is why like one of the reason why like this gamma is stated as part of the problem itself, because it's a 5 tuple. So some people like kind of ignore this discount factor, but this is important because it kind of it is a part of our problem. Some people like treat it as a hyperparameter, but that is in learning phase. But while we are solving MDPs, like this can play a very large role because changing gamma can essentially change our optimal policy also. So it can actually affect optimal policy. Okay, then again, like question six is asking, consider the following statements for a finite MDP. So I is the identity matrix with dimension. Okay, so this we have already seen in one of the questions also which we solved, identity matrix of 3 by 3, because there were 3 states. So dimension is this. P pi is a stochastic matrix. We have already seen this in that question, how it was formulated. So the point they are asking is which of the following statements are true. So, so first point is MDP with stochastic rewards. Okay, stochastic rewards are there, may not have a deterministic optimal policy. So this is definitely incorrect because like it's a well-known fact. So it's a fact actually. And MDP always has a deterministic optimal policy. It might it might be possible that it might not have stochastic policy. And if it has a stochastic, like the point is like it will always have a deterministic optimal policy. So this is a well-known fact. And I think this was discussed in class also. So may not have doesn't make sense. It will always have. There can be multiple optimal stochastic policies. Yeah, like this is true, right? Like I mentioned once also that argmax, right? It can return many actions. Then uh, either you can map to one of them, or suppose uh, if our Q table was like this. So we are considering just one state, right? Maybe S1. And this is A1, A2, A3, A4, A5. So the values are 2, 1, 2, 1, 2, right? So the argmax will return A1, A3, and A5. So while choosing a policy, you can either choose like by S1, you can choose it to A1, or you can say that when you are in S1, do A3, or when you are in S1, then do A5. But you can do this in a stochastic manner also, right? You can say that with zero point 0.3 probability you take A1, zero point 0.4 you can take this one, zero point 0.3, and these numbers you can vary because like all are optimal, all are like related to the same value too. So no matter like how you distribute the probabilities, it is always the answer will always remain the same. So this is kind of true, right? There can be multiple optimal stochastic policies. There can be multiple even deterministic policies also, right? If you map to just A1, you can map to just A3, you can map to just A5. So in this way, like this is one deterministic policy, this is another, this is third one. But you can have stochastic also by like simply redistributing these probabilities in a different way. Now, again, the question is related to gamma. Then the rank of a matrix is equal to. Okay, so rank of a matrix is equals to number of non-zero eigen values. And there was a discussion in class where like the professor also mentioned that this matrix, like it can, like suppose if we consider this I minus gamma, like you remember like Green's equation, we were taking inverse of this entity, right? And there was a reason given that this is invertible, like we were considering that the fixed point is unique. So the fixed point was unique because there was an unique solution. And that unique solution existed because this matrix itself was invertible. And this matrix was invertible because none of the eigenvalues were zero. None of the eigenvalues were zero. So if none of the eigenvalues are zero, so all are non-zero. So if all are non-zero, then the rank of the matrix will be equal to number of states. Because like you know this I is of dimension s cross s, and similarly p pi is also of dimension s cross s. So like there will be like these many number of states time eigenvalues. So that many non-zero eigenvalues are there. So definitely like its rank is equal to less than no. So you can get the answer from here. Like which of the following statements are true? If there is any doubt, you can ask. Otherwise, like I'll move to next question. Okay. So seventh question. Okay. So this is like similar to the question which we did in problem solving section also. But here the values have slightly changed. So maybe I'll show you like, so what was the green equation? Green equation was V pi is equals to I minus gamma times P pi inverse and R pi, right? So you just have to like find out the values. Just fill the values and take the inverse. So identity matrix as usual, this is 1, 0, 0, 0, 0, 1. And then minus, what is the gamma here? Gamma is 0.7. So there it was 0.9. And then like the policy which we are given is A to C and B to A and C to B. Okay. So accordingly, you can form this stochastic matrix also. So here, like you can see, like the policy is, what is the policy? Policy is deterministic, right? We are moving to just one state. But if it was like stochastic policy, then instead of having zero for all others and one for just one of the movement, you'll have to insert those probabilities. So like here, like our job is simple. So we just have to see like where to place one. So first column corresponds to A, so it will be 0, 0, 1 because we are moving to C, and for other two states we are not moving, then B, we are moving to A. Just a minute. So here like we can see B, we are moving to A, so it will be 1. So 0, 0 for other, and for C we are moving to B. So this will be our stochastic matrix. And this calculation, once you do, you will take the inverse of it and then multiply by this vector. So what is this vector for us? So A to C, where is A to C? A to C is 1. So first element of this vector will be 1. Then comes B to A. So where is B to A? B to A is 5. And third element is C to B. C2V is 10. So you take the calculate the inverse, first calculate this complete matrix, then take the inverse, then multiply it by this vector and you will get the answer. So this you need to do it yourself.
Sir,
Yeah,
I have
tell
doubt
me.
in question number 6.
Question number sixth. Yeah.
Yes. Wouldn't the first statement be true?
First statement. No, no. Like it's a fact that an MDP will always have a deterministic optimal policy. This is a proven fact. Like
But the
without,
second statement says that it can have multiple stochastic policies
yeah,
optimal.
yeah. So multiple stochastic policies can happen, but deterministic policy will be there, definitely there. So the second statement is not saying that there is no deterministic policy, right? It is simply saying that there can be multiple optimal stochastic policies. It is not showing that not saying that there will be, there can be multiple stochastic policies, right? So it is possible that, like, see, deterministic optimal policy will always be there. So you can always count that like an MDP is definitely having one deterministic optimal policy. Now, with respect to stochastic policies, you can have more than one. So mm, showed this example, right? You can like suppose if optimal action is like A1, A3, or A5, you can distribute the probabilities any way you want, and you will have multiple stochastic policy. And it's also not showing, saying the first option is not showing that it will have only just one deterministic optimal policy. Just saying that it will definitely, the fact is that will always have a deterministic optimal policy, can have more than one, but all those will map to the same B star. That is the point. Okay, I hope you understood it.
Yes, sir. Sir, can
Okay,
you briefly just explain the difference between deterministic and stochastic policy? Just
okay, okay.
shortly.
Yeah, yeah, right, right. So maybe I'll explain it here. So suppose a deterministic policy means suppose you are in some state S1, right? You take an action A, you will only go in S2. So this is like your deterministic policy. So basically this means is, so what is a policy? Policy is a mapping from state to action, right? So, or like this is in case of deterministic policy. So deterministic policy means like for one state, you will do only one action. Suppose it had the option of taking action B, action C, but it took only A. So this is deterministic policy, that while you are in state S1, you will take only one fixed action, that is A. So this is deterministic policy. But stochastic policy is the mapping from some probability distribution over the action set. So maybe it's like with zero point 0.2 probability you will take action A, with zero point 0.3 probability you will take action B, and with zero point 0.5 you will take action C. So it's not like, in this case it's like with deterministic, it's like A you are taking with one probability, B you are taking with zero probability, C with 0. So only one of the action you are taking certainly, and others you are not taking. So this is deterministic. But if it's like distributed across multiple actions, then it's called stochastic policy. So this is the difference between deterministic and stochastic policy. I hope
Sir,
you got
so
it.
what will be the deterministic policy in the ghost example?
In the ghost example, so deterministic policy in the ghost example, maybe I'll go there. We constructed that MDP, right? So there is this MDP. So we actually found this also, right? So if you are in laughter state, then play organ. So play organ like this has two variants. So there will be two deterministic policy. So if you are in laughter state, play organ and burn incense state. If you are, you can do this also. So this is like one optimal policy, pi 1 star, and this is another policy, pi 2 star. So in this, like play
Okay,
organ is definitely there, and you can not burn incense state. But when you are in quiet state, there is only one thing you need to do. So here, like if we had two options here, then there will be four optimal policies, right? But here, like we don't have a choice. We simply have to not play the organ and burn the incense stick. And same here. So
okay,
there
sir,
are
got
two.
it.
Okay. Yeah. So
Yes.
now I'll move to question number 8. So question 8 says that suppose x is a fixed point of function a. So it is given that x is a function fixed point of function a. So basically this means that ax is equals to x. Y is the fixed point of function b. So by is equals to y. And x equals to bax. Okay. So x equals to bax. So first we calculate this ax. It is given ax is equal to x, right? So x is also given equals to, so this ax will become x from here, right? So it is also given that bx equal to x. So x is fixed point of b also from this. So consider the following statements. So first option either way is x is a fixed point of b. Is this true? Yeah, it should be. But x equal to y need not be, right? Okay. This could have multiple fixed points also. See, you remember like when we were discussing unique fixed point, we consider a lot of restriction like Banach space and Cauchy sequence. So all those things, those need not hold here. So there can be multiple fixed point also. So B has a fixed point X also, Y also. It need not be that X equal to Y. So this is wrong. But if it was like those conditions were mentioned that it is like Banach space, Cauchy sequence, and all those things are being followed in this operator, and the norm also is this. So then it might happen. But this is a general question. And is it like BAY equals to Y? But BAY, we don't know how, like whether this Y is a fixed point of A. We don't know. So we cannot say that. So this is also. And what they have asked is must be true, always be true, right? It could happen, these two, but must be like it should always happen. That is not sure. So again, like the ninth questions is about norms. Again, like these are like these two questions are like simple plain algebra questions based on the concepts which have been used in class, but these are not related to reinforcement learning. So which of the following is not a valid norm function? Okay. So what are the like properties of norm? First property is suppose a vector is there, then its norm equals to 0 if and only if that vector is itself a zero vector, like all of the components are zero. Second, inequality. Second condition was like if we have a scalar and we are multiplying by this scalar, then the norm of this vector will be equals to you take like this is absolute value of alpha because it can you can multiply by negative also, right? And alpha is a scalar. And the third condition was the well-known triangle inequality. So you just need to check like which of the following like these satisfy all three of these properties. If it satisfies, then definitely it's a norm. And the triangle inequality basically says that norm of x vector plus y vector is lesser than equals to norm of x vector alone plus norm of y vector alone, right? So maybe like I'll explain this in vector spaces. So suppose this is a x vector, this is a y vector, right? So this will be x plus y, right? And norm is what? Simply the length, right? If we are considering L2 norm. So we can put this x vector, just translate it to here. So this is y vector, x vector. So this forms a triangle in this way. So you know that the sum of two sides of a triangle is always larger than the third side. So in this way we get this. So this is like norm x, this is norm y. So sum of these two is greater than norm of this. So this way, like this triangle inequality comes. Now the question they are asking is which of the following is not a valid norm function. So if like you have done some course, you might know. Actually, this is actually covered in the lectures also. This is the max norm. So this is definitely a norm. So this is a norm. So they are asking not valid. So this is valid actually. So this is max norm, simply taking the maximum absolute component. Uh, Do you know like what this norm is? Like this is a famous norm. Maybe write in chat.
L2 norm.
Yeah, this is the L2 norm, famous norm. So it's a norm either way. So again, like you cannot say this is not a valid norm. And this norm, do you know?
Fourth one,
Yeah, fourth one.
L1 norm.
Yeah, this is the L1 norm. So this is also a valid norm. So I mean like minimum, but minimum you can see like what is the issue. So like this condition, first condition gets violated in this. It can be zero even if like this is not zero. Suppose you consider a vector where like some of the elements are like 1 minus 1. So it's still like minimum can be zero, right? But the vector itself is not a zero vector. So uh, I mean like 2 probably. So the minimum. Either way, like it was considering absolute value, so minus 1 also makes sense. So this is not the valid norm. So now, like again, like the third question, again, not related to reinforcement learning, but related to concepts which are used in the lectures. These are from algebra. So which of the following is the contraction mapping in any norm? So the this is the point, main point that in any norm, regardless you can take L1 norm, L2 norm, L3 norm, or L infinity. This is known as max norm. Whatever norm you take. In fact, like these norms have a specific formula, right? So D is equals to 1 to capital D, like whatever elements are there. And this summation you take and you raise it to, suppose if it's LQ norm, then you raise it to Q power. And after taking that summation, you take 1 by Q. This is the general form of a norm. Now, what they are asking is for any of these norms, like in fact, like the norm needs not follow this structure also. There could be norms which go beyond this structure also. So just the condition is that these three conditions should hold. Then no, it's a norm. You might have heard of KL divergence. So it's not because it's while it's one of the condition symmetry basically. So either way, leave this out. So the question is which of the following is a contraction mapping in any norm? So zero point 0.5 and zero point 0.5. So what we are doing is basically like we are multiplying by zero point 0.5 each component and will it get shrinked? Let's see L2 norm maybe zero point 0.5 square times x1. So if we take it out, it will be zero point 0.5, right? X1 square plus x2. So this is the original distance and it got shrunk by a factor of 0.5. And in a similar way, you can check for L1 norm also whether the same thing is happening. It will happen definitely. In fact, it will happen for any of the norm because you are simply like, suppose if you take L3 norm, you are cubing it, then take cube root, then this comes out. So either way, like this will definitely we are contraction norm. Now, is this so contraction basically means that this factor which is getting multiplied is less than, suppose if it's lambda, it's less than 1. But in this case, it will be actually expansion will be happening, right? Because this factor is 2. So it's 2 means something more is happening. So it's not contracting, it's actually expanding. So this is not right. And again, like similar kind of step you can do here. So like it's kind of expanding here also. So this is not happening. Now, like maybe you can say like whether this is a valid norm x1 plus x2, x1 minus x2. So just take x1 equals to 1 and x2 is equals to also 1. So what would be the L2 norm? L2 norm will be root 2, right? And what will be norm of this one? So this will become 2, 0. So again, like its L2 norm will remain 4, right? 2 square, yeah, it will become 0, then it will become 4. So basically 2. So after application, it actually got expanded, not contracted. So again, like this is not a valid norm. So I hope like you got this also, right? If there is any doubt, like you can ask me. Otherwise, like I'll move to the next section. So next section is basically like the reading material. There's not much reading material. So in the previous lecture, you I think already covered till section 3.5. So for the remaining sections, you can read this Sutton and Bartu book. And then like there is a chapter 4 which is dynamic programming. This contains all those value iteration, policy iteration. Probably LP, I think, is not there in the Sutton and Barter book. So maybe you will have to do it on your own, or maybe if it's there in the lecture, then maybe you can do it. But this is also a popular method of solving those Wellman optimality equation. So keep reading these chapters from Sutton and Barter book also. So I think that was it from my side today. If there is like any doubt before leaving, you can ask me. Otherwise, like I'll close this session. Okay, I'll see chat. Yeah, welcome.
Thank you.
Yeah, welcome. Okay, so probably I want to make an announcement. I'm not sure about this one. But generally we have our sessions on Tuesdays, right? So the next session we were supposed to have on 27th, but since I am traveling, so I might prepone it to Friday, but it's not confirmed yet. So Friday means 23, just like 4 days from now. So we might have a session on Friday. So it's getting preponed, not postponed. So you'll have to be careful of that. So it might be conducted on 23 Friday, but if it gets confirmed, you will get a notification also that it got preponed. I'm not sure about it. If that request gets accepted, then it will be on Friday, not Tuesday. Okay, so that was it from my side. I'll stop sharing my screen now. Yeah, maybe I'll stop recording. Okay, then bye everyone. See you on Friday, possibly.